So this is the last section of new material from Chapter 8 that you're responsible for, and it's on graphing inequalities. And just like the last section, doing a light version of this, it's completely adequate for what you're going to ever see in terms of this topic. But this can get quite a bit grungier than I'm going to make this section for what it's worth, but this will be completely good enough. Before I jump into the section, we have to remember how to graph some lines, and specifically these kinds you may have forgotten how to do, so I should do them first. So if I asked you to graph the equation x equal to 3 or x equal to -2, this is not an inequality. It's an equation because it doesn't have a less than, greater than, less than or equal to, or greater than or equal to. When we get physically into section 8.6, every problem is going to be a graphing problem, and it's going to have a less than or greater than symbol of some sort. And the graphs are going to be a little bit more complex than graphing an equality, but not terribly much more. To graph the equation x equal to 3, I have to remember that if an equation only has an x, that the graph is a straight up and down vertical line as opposed to horizontal. So to graph x equal to 3, the equation x equal to 3, I'll find 3 on the x-axis, draw a vertical line through the 3. If I want to, I can label the x-intercept. When we're doing this section, it's going to be important as I graph to label x-intercepts. So I'll get in the habit of doing that, even though this problem's not physically from the section. And then just so to make sure you remember why we call this the line x equal 3, it's because no matter what point I mark on this line, it's actually supposed to be the point 3,4, this is the point 3,2, maybe this is the point 3, -1. The reason we call this the line x equal 3 is because every single point on the line, its x coordinate is 3. If I want to graph x equal to -2, it's not really any more challenging. I would just find -2 on the x-axis and draw a vertical line through -2 on the x-axis. Putting arrows at the end of my line that I'm drawing saying the graph goes on forever is nice, but it's not a deal breaker if you don't put those. Labeling the x-intercept is going to be important for some of the problems in this section, so I went ahead and labeled it. An important line that we're going to draw a lot in this section is x equal to 0. And x equal to 0, when you graph it, it graphs to be the y-axis because it's a vertical line through 0 on the x-axis. Let me just draw x equal to 0 for you real quickly. So if I want to draw x equal to 0, I'd find 0 on the x-axis, and this is the x-axis, and the 0 on the x-axis is there, and I draw a vertical line. So that is a graph of x equals 0, which is the same again as the y-axis. So none of these problems would be problems that come up in 8.6 because every problem in 8.6 has an inequality symbol. All of these have an equal sign, which is not an inequality, it's an equality. But nevertheless, you need to be able to graph equations that only have x before we get into section 8.6. And similarly, you need to be able to graph equations that only have y. And so I should do those too. So just, and I guess if you know one, you get the other. So if I want to graph equations, I'll worry about the less than and greater than signs here in a little bit, with only a y. So if I wanted to graph something like y equal to 5, To graph y equal to 5, I would just find 5 on the y-axis and draw a horizontal line, a line parallel to the x-axis. So this, if I'm going to draw the line y equal to 5, I find 5 on the y-axis, draw a line parallel to the x-axis, horizontal line. I like to label the intercept. In this case, there's a y-intercept at the point 0, 5. Wouldn't need to draw any additional points on this, but I could if I wanted to. And what the points would have in common if I started drawing more points, like if I made this point, which maybe is the point 25, this point, which is maybe the point 45, maybe go out here, this point, which is the point -2, 5. What those points have in common, as every point on this line will have in common, is that the y-coordinate of this line is 5. So the reason I call this y equal to 5 is because every single point on the graph has a y-coordinate of 5. Lastly, let me do y equal to 0. To graph y equal to 0, I'll find 0 on the y-axis and draw a horizontal line. This is my y-axis. 0 on the y-axis is in the same place as 0 on the x-axis. So the line y equal to 0, I find 0 on the y-axis and draw a horizontal line, and I get that graph. And that actually is the equation of the x-axis. It always feels like it's wrong to me. Like the equation of the x-axis should have an x in it, the equation of the y-axis should have a y in it, but it doesn't. So the equation y equal to 0 graphs to be the x-axis. So that you may have forgotten. Equations with only x's graph to be vertical lines. Equations with only y's graph to be horizontal lines. Ultimately, every problem in section 8.6 is going to have, it's going to be a two-step problem. The first step is to graph a line and then to shade. So let me do problem 4 before number 2 because it somehow, the equal sign makes it easier. So this is the beginning of the actual section 8.6 lecture. And what problem 4 wants me to do, then I'll go back and do problem 2, is to graph or indicate or show or identify all points that have x coordinates that are greater than or equal to -5. To do this, it's easy for me to show this part. I can show all the points on the coordinate system that have x coordinates equal to -5 because that's going to be any point that's on the line x equal to -5. For each problem in this section, I'm going to start off by graphing the equal line in some sense. So first, to do this problem, I'm going to graph the equal part. So I'm going to graph the line x equal to -5 because I'm supposed to identify all the points that have coordinates, x coordinates that are either greater than or equal to -5. And this would be identifying all the points that have x coordinates equal to -5. Its x-intercept was the point -5, 0. It's supposed to be a perfectly vertical line as opposed to a slanted line, but didn't kind of turn out that way when I graphed it. The rest of my finishing up problem 4 is to get this part done, identify all the points that have x coordinates greater than -5. And that's easy to do because I can look at the coordinates of any point, and if I go to the left of this vertical line at x equal -5, the x coordinates of the points are going to be -6, -7, -8, -6.5, -6.25. Any point that's to the left of this line, like here the point -7, 1, its x-coordinate isn't greater than -5, so this wouldn't be a point I want to identify. But a point like this, maybe the point -2, 4, if that's what that point happens to be, or this point -3, -6, or this point 1, 1, what each one of these points have in common, if I look at their x-coordinate, it's bigger than -5. It turns out that in this section, it's always going to be the case that one side of the line makes the inequality true, and the other side of the line makes the inequality false. So in this particular line, I'd say this is the false side, because every point to the left of the line, if you look at its x-coordinate is going to be less than -5, and I'm trying to identify the points of the graph that have x-coordinates greater than -5. And so that's the false side of the line. By default, that's going to make this side of the line the true side, which means any point to the right of the line is going to have an x-coordinate that's bigger than -2. And to identify all the points that have x-coordinates greater than -5, we shade. And I'm going to shade all the way from my line all the way to the far right edge of my graph. My shading's not supposed to stop. It's supposed to go on forever, but eventually you just have to stop. So this would be a pictorial representation of all the points that have both x-coordinates equal to -5 and x-coordinates greater than -5. The vertical line shows all the points that have x-coordinates equal to -5, and the shading to the right of that vertical line shows all the points that have x-coordinates greater than -5. So I've accomplished my goal. I've identified all the points that have x-coordinates that are greater than or equal to -5. Problem 2 that I skipped over asks me to identify all points that have x-coordinates greater than 5, but not equal to 5. Unlike the last problem, where the inequality had the or equal to, this one doesn't have the or equal to. It'd be real tempting probably to do this problem by drawing a vertical line that goes through 6, because 6 is maybe the first number you can think of bigger than 5. But if you did that, if you started off drawing a vertical line through 6, you're not going to be identifying all of the numbers greater than 5, all of the points that have x-coordinates greater than 5, because a point that has an x-coordinate like 5.25 or 5.75 or 5.1 would be points on the graph that have x-coordinates greater than 5. So to do this, I'm going to graph the line x equal to 5, which is somehow kind of the boundary number here. But I'm going to draw it with a dotted or a dashed line, meaning that that's the boundary of my solution, but it's not included in my solution. So to start off problem 2, I'm going to find 5 on the x-axis, because that's an important line, or important number. It's the only important number. And I'm going to draw a dotted line. Every point on this line, which has x-intercept of 5, 0, its x-coordinate is equal to 5, and I don't want to identify those, so I draw a dotted line as opposed to a solid line, because that means I'm aware this is an important line, but it's not part of the solution, because points on this line have x-coordinates equal to 5, and I don't want to identify those. But somehow any point to the right of this line, like this might be the point, 5.25, 1. This might be the point, 5.1 comma 6. Any point to the right of this line, the points are going to have x coordinates greater than 5, and even right up to the line. So what I'm going to notice for this, just like the last problem, the false side of the line is going to be the left side, because any point to the left of this line, like this point may be the point 2 comma 3, its x coordinate is a number that's going to be less than 5, and this, the right side of the line, is going to be the true side. And to accomplish my goal, identifying all the points that have x coordinates greater than 5, that's going to be any point that's physically to the right of this dotted line. Because any point to the right of the dotted line is going to have an x coordinate of 5 point something, or 6 point something, or 7 point something, or 6, 7, 8, or a million. It's going to be bigger than 5. So this would be the graph of number 2 that would be considered correct. So in general, when I'm graphing an inequality with only an x, so I'd say rules for graphing an inequality, that doesn't means we don't have an equal sign, of a problem that only has an x, so there's 4 scenarios. We could have an x greater than some number, an x greater than or equal to some number, an x less than some number, or an x less than or equal to some number. For each one of these, I'm going to start off by drawing the line x equal to that number. So for each one of these, for this scenario right here, the first thing I'm going to do is I'm going to draw x equal that number, but I'm going to make it a dotted line because my inequality doesn't have the or equal to. And if I'm trying to identify numbers that are greater than a specific number, for the x-axis, greater is to the right. And for this particular scenario, this is just the scenario of problem 2. Problem 2, I graphed x equal to 2 with a dotted line, and I shade to the right. The reason the dotted line, because the inequality doesn't allow for the equal. The reason I'm shading to the right is because greater than numbers get bigger as I go to the right on the x-axis. Problem 4 that I started off doing, my first step was to graph x equal to the number. In my case, it was -5, and I do it with a solid line. And again, because I want to identify points that I have bigger x coordinates than some number, I'm going to shade to the right. So these kind of model the problems 2 and problem 4. Problem 2, when I graphed x is greater than 5, this is what I did. I drew the line x equal to 5. I found 5 on the x-axis, drew a dotted line through x equal to 5, and then I shaded to the right. That identified all the points on the on a coordinate system whose x coordinates were greater than 5 but not equal to 5. When I did problem 4, when I identified all points at x coordinates that were equal to -5 or greater than -5, I followed this. I haven't got to less thans yet, but less thans and less than or equal to's won't be that different. To graph x as less than to some number, the first thing I'm going to do is I'm going to graph x equal to that number, but because this doesn't have an or equal to, I'm going to draw a dotted or a dashed line. I don't know, it doesn't matter what you call it. It's just not going to be a solid line. And my shading is going to go to the left because I want to identify points less than a specific x value, and on the x-axis numbers go smaller as I go to the left, so I'm going to shade to the left to finish up my graph. And then the last situation I might have for an inequality with only x is a less than or equal to symbol, and in this case I'm going to graph the x equal to that number with a solid line because it's allowing the or equal to part, and then I'm going to identify the less than part by shading left. So when I get back into the section, any inequality that has only an x and not a y, I'll follow the rules here. Specifically, I'm going to draw a vertical line. It's either going to be dotted or solid. Solid if I have the or equal to, dotted if I don't have the or equal to, and then I'm going to shade right if there's one of the greater thans. I'm going to shade left if it's one of the less thans. So there's hard and fast rules for drawing equations of inequalities that only have x's written in the form x is greater than some number or x is less than some number, which is all we're going to see for inequalities with only x's in our section. So problems 6 and 8 are inequalities that only have x's. Problem 6 wants me to draw x is less than 6 to identify all points that have x coordinates that are less than but not equal to 6. To do this, I'm going to find 6 on the x-axis, and I'm going to draw a dashed vertical line. The line x equal to 6 would be a solid vertical line through 6, but I don't want to include the or equal to part of this. So I'm drawing a dashed vertical line through 6 on the x-axis. Now I want to identify points that have x coordinates less than 6, and to the left of 6 the numbers on the x-axis are less than 6. So I'm going to shade, physically darken in. I can get darker with my shading than I've been if I want to, but I don't have to. Physically supposed to completely darken this in, but eventually you just get tired of, darkening. This is maybe a better shading job than I did last time. But that would be a picture that identifies every point on the coordinate system that has an x coordinate that's physically less than 6, although my graph's not supposed to go over that dashed line. And this dotted line means that the line x equal to 6 isn't part of the solution, but it's a boundary of the solution, because a point right next to the line might have an x coordinate of like 5.99, comma, say negative 6 down here, and that point would need to be indicated with my shading because its x coordinate is less than 6, and that's perfectly done. To do number 8, to draw all points that have x coordinates that are less than or equal to negative 1, I start off, I find negative 1 on my x-axis. I draw a solid line because of the or equal to part. And because I want to identify points that have x coordinates less than negative 1, I'm going to shade to the left. Inequalities that only have x's, less than you shade to the left, greater than you shade to the right. They're really constant and nice that way. And when I shade, I can get as detailed as I want or as dark as I want. I can physically shade so that you don't even see the axes, and that would be adequate as well. Generally, I don't get that elaborate with my shading, but if you want to, you use a highlighter, you can darken in the area real nicely. So those are the first few problems. They're inequalities that only have x's, and they kind of follow similar, they all follow a mold. For the next few problems, 10, 12, 14, and 16, I have inequalities with only a y. The rules are going to be similar and constant. So these are nice sets of problems. So the next few problems, I'm going to be dealing with inequalities, which means I don't have equal signs. When I'm graphing an inequality in 2 dimensions, I have to shade. There's going to be 4 kinds. They're going to be a y greater than without an or equal to, a y greater than or equal to, a y less than, and a y less than or equal to. For each one of these scenarios, when I go to do my graph, there's hard and fast rules. Very specifically, for all 4 of these, I'm going to draw a horizontal line, because when an inequality only has a y and doesn't have an x, the graph of the y equal part is a horizontal line. So for each one of these, I'm going to start off by drawing a horizontal line. And in this top scenario, I'm going to start off by drawing a dotted or a dashed horizontal line. That's going to be the boundary. And if I want to identify points that have y's bigger than some number, because the y coordinates get bigger as you go higher on the y-axis, I'm going to shade above the line or shade up. Because above y's, the higher you go, the bigger the y's get. Greater than implies higher in terms of the y, and it implies to the right in terms of the x's. For this next scenario, having y greater than or equal to some number, I'm going to start off drawing a solid as opposed to a dashed horizontal line, a line that's parallel to the x-axis, and similarly I'm going to shade up because I'm trying to identify y coordinates that are greater than some number. The bottom two I'm going to wind up shading down because I'm looking for less thans, and y's get smaller or less than as you go down. And then for the solid and the horizontal, the solid and the dotted, in this top version that doesn't have the or equal to, I'm going to draw a dotted horizontal line. Because I don't see the or equal to. And again, if I'm going to try to identify points that have y coordinates less than some number, less than on the y-axis is down, because numbers on the y-axis get smaller as you go down. And then the last scenario, y is less than or equal to some number, I'm going to draw a solid horizontal line. And I'm going to shade down again. The inequalities with only x's or with only y's are the easy part of this section. The inequalities that we'll get after these have both x's and y's, and they're harder because the graphing it's harder to do the graph of the line part, and it's harder to do the shading part. Everything about them is harder. But the inequalities that only have an x or only have a y, I can mindlessly graph these quickly. So getting back to the section, problem 10 wants me to graph all points that have y coordinates greater than 3, and that's not hard to do. To graph number 10, y is greater than 3, I'm going to draw the line y equal to 3, which means I'm going to find 3 on the y-axis, and because I don't have the or equal to, I'm going to draw a dashed horizontal line as opposed to a solid, and that would be the line y equal to 3. I don't want to include points that have y coordinates of 3. The dashed line omits those points. And now I want to also identify points that have y coordinates greater than 3. And if you look at the y-axis, going up the y-axis, the numbers 4, 5, 6 get greater than 3. So I'm going to shade up forever. And this would be an adequate shading, although maybe not as dark as you might like it, but a shading that works fine. That would be a good picture for all points on the graph that have y coordinates that are bigger than 3 but not equal to 3. The dashed line omits the y equal to 3 part. The shading up gives me all points that have y coordinates greater than 3. For number 12, graphing all points that have y coordinates greater than or equal to -6, the first thing I do is find -6 on the y-axis. A lot of times when I do my shading in this section, I don't do real good jobs of incrementing on my x and y axes, and this would be an example of that. Rather than writing -1, -2 all the way down to -6, I just make it a -6 on the y-axis. I'm drawing a solid horizontal line through that -6, a solid line as opposed to a dashed line because of the or equal to part of this. And then the shading is going to go up because it's greater. I want points that are greater than, have y coordinates greater than -6, and that's going to be above that line. Again, you can shade as well as you'd like to shade, but that would be more than adequate. So the difference between 10 and 12 is they're both greater thans, and they only have y, so they both shade up. 10 has a dashed line, 12 has a solid line, because 10 doesn't have the or equal to, 12 does have the or equal to. 14 and 16 are y's only with less thans. And to do 14, I'm going to find -1 on the y-axis because I'm asked to graph y is less than -1. Inequalities with only a y are still horizontal lines, so I'm going to draw a horizontal line through y equal to -1. Be nice if I labeled the y-intercept at 0, -1. Because this is a less than, I'm shading down as opposed to up. And any point underneath that line, its y-coordinate is going to be less than -1. And then lastly, the y less than or equal to 0, I'm going to find 0 on the y-axis, which is right there. Draw a solid line that you're not going to be able to see so well. There's my solid line. That's the line y equal to 0. The intercept, the y-intercept is 0, 0. And for a y only, if there's a less than, I shade down. A greater than, I shade up. This is a less than symbol. I'm going to shade down. That's the friendly part. So up through 16, I could have hard and fast rules. If I only have an inequality with an x, I get a vertical line. Dashed if it has no or equal to. Solid if it has an or equal to. If you only have an x, greater than is right, less than is left. With a y, less than is down, greater than is up. You get horizontal lines, dashed without the or equal to, solid with the or equal to. Most of the rest of the problems have both an x and a y, and the one part that's similar with these is the dashed or solid part. So if I'm doing problem 18, I'm asked to identify every point on the graph that if I add its x and its y coordinate, I get a number physically less than 6. I'll do this in 2 steps. First, I'm going to graph the boundary, which is the line x plus y equal to 6, and I'm going to graph it with a dashed line. So step 1, I'm going to graph the boundary, which is the line x plus y equal to 6. And I'm going to do that graph with a dashed line because the inequality doesn't have the or equal to. And all of a sudden I switched my name from dotted to dashed, and just means it's not a solid line. And very specifically, there's lots of ways to graph this particular line. The best way to do the graph for this particular section is to find both the x and the y intercepts. And so I'm going to do that. I'm going to graph the x and the y intercepts by plugging in 0 for x and solving for y, plugging in 0 for y and solving for x. So for each of the inequalities that have both x's and y's, I'm going to start off by graphing the boundary. It's going to be a dashed boundary if you don't have the or equal to. It's going to be a solid boundary if you have the or equal to. And it's going to be best to find the intercepts. So if into the boundary I put 0 for x, I'd go 0 plus y equal to 6. That's going to give me y equal to 6. One of the points I'm going to graph is the point 0, 6. If I plugged in 0 for y, I'd get x plus 0 equal to 6, which gives me x equal to 6. The second point I'm going to draw is the point 6, 0. So the beginnings of this problem is to find 6 on the y-axis, label the point 0, 6. 6 on the x-axis, label the point 6, 0. And connect those 2 points, but not with a solid line, and do it with a dashed or a dotted line. And every point on this line, it's going to satisfy x plus y equal to 6. Some points on this line that I haven't labeled would be like the point 5, 1, because 5 plus 1 is 6. Similarly, that's probably the point 1, 5, I guess. Maybe this is the point 5, 1. But the kind of points on this line are points like 0, 6, 1, 5, 2, 4, 3, 3, 5, 1, 4, 2. Every point on this line satisfies the inequality, satisfies x plus y equal to 6. You might have a point like 7, -1. It's not necessary to label any more points than the x and the y intercept, but if I did label more points, they'd all have this quality that if you add the x and the y, you'd get 6. So step 1 is to graph the boundary. Step 2 is to figure out where to shade. Every problem that's an inequality that I graph in 2 dimensions, I'm going to shade, and we're only doing lines. So I'm either going to shade one side of the line or the other side of the line. There's always going to be a true side of the line and a false side of the line. And every problem that we do that only has an x and a y, it's going to be real easy to figure out which side is the true side of the line and which side is the false side of the line by doing the same test for every problem. Very specifically, I'm going to test the point 0, 0 in the original problem. So I'm going to test the point x equal to 0, y equal to 0 in the original problem. X plus y is less than 6. And by testing, I'm going to plug 0 in for x, 0 in for y, and see if I get a true or a false statement. If I get a true statement, then 0, 0 is on the true side of the line. If I get a false statement, then 0, 0 is on the false side of the line, because there's always a true and a false side. When I did the math here, I got the statement 0 is less than or equal to 6, which tells me that 0, 0 is on the true side of the line, and that the opposite side of the line, the side of the line that doesn't contain 0, 0, is on the false side of the line. And what I want to do is I want to shade the true side. And by shading, I'm going to go all the way from my line all the way to the entire graph, across the axes and everything. And darken in your shading more if you care to darken it in more, or completely darken it in. So that would be a picture, an adequate picture of the line x plus y is less than 6. So I started off, I graphed the boundary with a dashed line because I didn't have the r equal to, and then I figured out the true side of the line because every inequality has a true side and a false side. I need to shade the true side. 20 wants me to graph the inequality 4x plus 3y is greater than 12. So step 1, I'm going to graph the boundary. Which is going to be 4x plus 3y equals 12, and I'm doing a dashed line because I don't have the or equal to part of this. And for every one of these graphs, I'm going to let x equal to 0 and y equal to 0 and get my intercepts. So graphing this, there's many ways to graph this, but in this particular section, doing the intercepts is the most effective way. So if I let x equal to 0, I'd go 4 times 0 plus 3y equals to 12. This gives me 0 plus 3y equal to 12, which gives me 3y equal to 12. Dividing by 3, you get y equal to 4. So the y-intercept is going to be at 0, 4. And then if I let y equal to 0, I'd go 4x plus 3 times 0 equal to 12. The 3 times 0 would go away and leave me with 4x equals to 12. When you divide by 4, you'd get x equal to 3. So that would give me the point 30. So as I go to do my graphing, real crudely, I'm going to find the y-intercept of 0, 4 and the x-intercept of 3, 0. And our graphs don't need to be any more accurate than I'm drawing, so you don't have to get over, you don't need graph paper. I brought some graph paper for some of the ladder problems, but you don't need it, but just because we're going to be graphing 2 or 3 inequalities on the same graph, and it will make my graph prettier if I use graph paper. But for this particular problem, there is no need to use graph paper whatsoever. So I did my boundary with a dashed line. Step 2 is to finish it off by shading. I have to find the true and the false side of the line. I find the true and the false side of the line by figuring out if 0, 0 is on the true or the false side. I'm going to plot x equal to 0 and y equal to 0 into the original problem, I'm going to go 4 times 0 plus 3 times 0 is greater than 12. That simplifies to the statement 0 is bigger than 12. And because 0 is not bigger than 12, 0 is most definitely less than 12. 0, 0, because when I plugged it in, it gave me a false statement, then the side of the line that has 0, 0 is the false side of the line. By default, that makes the other side of the line the true side of the line. Every inequality, when you graph it, the graph has a false side and a true side. Plugging in 0 for x and 0 for y, seeing if the statement is true or false, tells me whether 0, 0 is on the false side or the true side. In this case, because 0 isn't greater than 12, 0, 0 is on the false side, makes the other side the true side. I finish up by shading the true side. And by shading, I go, as far as I care to go. The shading's not supposed to stop. It goes on forever. But eventually I just stop drawing because I'm not going to shade forever. Eventually you just get tired of drawing. But I'm just indicating anything to the right of that dashed line it makes the statement 4x plus 3y is greater than 12 true. If I picked a point out here, plugged the x and the y coordinate into the original inequality, it would make the statement true. If I picked a point down here, any point that's not shaded, plugged that point's x and y into the inequality, it'd make the original inequality false, is kind of what this picture shows. 22's lots of mess going on here. It has a couple minuses. So 22 wants me to graph the inequality 3x minus 2y is less than or equal to negative 6. Step 1, I'm going to draw the boundary of 3x minus 2y equals to negative 6. In this case, my boundary is going to have a solid line as opposed to a dashed line because of the or equal to. So even though this problem looks like it should be a lot harder, it's not really. So I'm going to plug some zeros in for x and y to get my intercepts. So into the boundary line, I'm going to go 3 times 0 minus 2y equals negative 6. This piece is going to zero out. I was going to leave me with minus 2y equal to negative 6. And if I divide both sides by negative 2, I get y equal to 3. So one of the points I'm going to plot is the point 0, 3. If I plug 0 in for the y, I go 3x minus 2 times 0 equal negative 6. This gives me 3x equals to negative 6 because that piece zeroes out. I divide both sides by 3, and I get x equal to negative 2. So now I'm going to plot the point negative 2, 0. So as I go to graph this, first step is to graph the boundary. The boundary line has an x-intercept at negative 2, 0, a y-intercept at 0, 3. And again, I'm just fudging on these. I'm not drawing them with any real accuracy. So this is the point negative 2, 0. That's the point 0, 3. Not that it looks like that, but that's what I've drawn there. And it's actually supposed to be a line and not have a wave to it, but hardly matters. Step 2 is going to be my shading. And again, I'm going to find out what happens when I plug 0, 0 in. If I get a true statement, I'll know 0, 0 is on the true side of the line. If I get a false statement, I'll know 0, 0 is on the false side of the line. So into the original problem, I'm going to plug x equal to 0, y equal to 0 into 3x minus 2y is less than or equal to negative 6. So I'm going to go 3 times 0 minus 2 times 0 is less than or equal to negative 6. This whole left side zeroes out, and I get 0 is less than a negative number. 0 is bigger than every positive number. That's a false statement. Saying 0 is less than a negative number is a false statement. Because when I plug 0, 0 into the problem, I get a false statement. That means 0, 0 is on the false side of the line, which means the other side of the line is the true side of the line. I'm asked to shade the true side of the line, so I'm going to shade the best I can. Not supposed to go over the line. And again, you just eventually stop shading. But anything above that line is considered the true side of the line. and that would be an adequate shading for number 22. So exactly the same steps, even though the inequality looked a little more imposing. I had minuses to the left of the inequality, minuses to the right of the inequality. I don't have to worry about doing any flipping. I'm not doing any algebra with the inequality, because when I'm graphing the boundary line, I'm not worried about the less than or greater than part. I'm only worried about the less than or greater than part when I'm doing the shading. And when I'm doing the shading, I'm just plugging in zeros for x and y, and there's no need to do any flipping. So the math is mild in this section. There's no factoring to do. It's moderately straightforward. So 24, the last one where it's moderately friendly. Graph the 4x minus 3y is greater than or equal to negative 24. So I'm going to start off, I'm going to graph the boundary. Actually it says boundary. And it's going to be a solid line because of the or equal to. And the boundaries, the 4x minus 3y equals to negative 24. And again, I'm just going to let x be 0 and y be 0. Plot the x and the y-intercept. When I let x equal to 0, I get 4 times 0 minus 3y equals to negative 24. The 0 piece cancels out. You're left with minus 3y equal to negative 24. When I divide both sides by negative 3, I get y equal to 8. So that's going to give me the 0.08. And when I do the other 0, I go 4x minus 3 times 0 equal to negative 24. The 3 times 0 piece goes away, leaves me with 4x equals to negative 24. Divide both sides by 4, and I get x equal to negative 6. So that's going to be the point negative 60. So when I go to graph these, again, I'm not being horribly accurate. I'm going to guesstimate the 0.08. I'm going to guesstimate the point negative 60. And I'm drawing a solid line because I have the or equal to. And now I'm going to worry about my shading. So this was step 1. And then I'm going to do step 2, which is my shading. And I'm going to try the point x equal to 0, y equal to 0, which is this origin. Figure out the true and the false side of the line. I'm going to go to the problem 4x minus 3y is greater than or equal to negative 24. Plug in 0 for x, 0 for y. This gives me 0 is bigger than a negative number. 0 is bigger than, that's a true statement, 0 is bigger than any negative number. And the last problem I had 0 was less than a negative number. 0 is never less than a negative number, but it is greater than a negative number because I get a true statement when I plug in 0, 0. That means the side of the line that contains 0, 0 is the true side, and the side of the line that doesn't contain 0, 0 is the false side. I always shade the true side of the line. And usually that's all I do for my shading. I don't physically darken it all in like with a highlighter, but you can if you have that at your disposal. So that's so we started off with only x's and only y's, then we mixed into x's and y's. The next few problems have two inequalities that I want to simultaneously graph on the same graph. Ultimately, what I'm going to do for the next few problems is darken or indicate where the shadings overlap. So the next few problems, 26, 28, 30, I'm not sure how high it goes, we're going to graph two inequalities on the same axes, and this is a nice time to have multiple colors. So I'm going to set up my graph, and I'm going to do two graphs on the same axes. The first thing I'm going to, really? That. Hold on, I'm in the process of changing this problem as we speak. Give me 2 seconds here to do this. Oh gosh, 3. I don't like this because this is not the kind of graphing I care to do right now. So let me make up a better one. 1 and 2 is okay. stumbling here to make this better for you for our first problem. 4 and 2. 4 and 2 is 32, 26, 8, 10. I'm changing problem 26 because I teach I'm allowed to make that change to make it, it's still a cruddy problem, isn't it? Really? Oh well, I'm dealing with the cruddy problem. Cruddy meaning it's going to have fractions, but not as cruddy as the initial problem. Yeah, I'd probably say yes, not as cruddy as the initial problem. So I'm changing the top one to be 8x minus 3y is greater than 26, and the bottom one to 2x plus y is less than 10. What I'm going to do, why I pulled out the multicolors, is I'm going to do each one of these separately, and then I'm going to darken or indicate where the shadings overlap. So I'm going to treat this as two different problems. I'm going to draw them on the same graphs. So I'm going to try to do this problem, which is going to be unpleasant in some sense because it's going to have fractions, and the initial problem was going to have fractions, but this one has less fractions, well, better fractions in some sense. So I'm going to do the same thing. My step 1 for this is to let x and y be 0. If I let x be 0, I'd go 8 times 0 minus 3y, and I'm doing the boundary, so I'm doing the equal 26, so I should have tried to crunch this down, but I should say I'm graphing the boundary, and I'm going to do it with a dashed line. The boundary equation is 8x minus 3y equal to 26. That's what I start off doing. And when I start off this, I get minus 3y equal to 26. Y equals to 26 over minus 3 if I divide both sides by minus 3. And I'm going to live with ugly decimals here. I'm going to round to 2 decimal places to guesstimate where I'm graphing. If I do 26 divided by negative 3, I see negative 8.66. So when I go to graph this negative 26 over 3, because it's negative 8.66, on my axes, I have negative 8, then negative 9, and this point right here, negative 8.66, this is going to be the point 0, negative 26 over 3. Sorry for the fraction there, but I needed to have a decimal idea of what that fraction was, which was negative 8.66, and when I plotted that point, because it's a y-intercept, I plotted it in between closer to negative 9 than negative 8. The next one, when I plug my 0 in, I'd go 8x minus 3 times 0 equals to 26. This gives me 8x equal to 26. And when I divide both sides by 8, I get x as 26 over 8, which I'm going to reduce by 2 to 13 over 4. So the x-intercept is 13 over 4 comma 0. And again, I'm going to do 13 divided by 4 on my calculator, which gives me 3.25. So when I plot that point, that hardly looks like 3. 1, 2, 3, 4. So when I plot that point, 13 over 4 comma 0, that's about there. It's in between 3 and 4. And I'm drawing this with a dashed line. So first, unfortunate decimals to deal with, but they're not that hard to deal with. You can make your fraction into a decimal and then approximate where that shows up. So the negative 26 over 3 was negative 8.666. The 13 over 4 was 3 1/4. So that's the beginnings of graphing this. Now I need to shade. So I'm going to sneak in my shading here. I'm going to do x equal to 0, y equal to 0 into this. I'm going to go 8 times 0 minus 3 times 0 is greater than 26. This is going to give me 0 is bigger than 26, and that's a false statement, which means the point 0, 0 is on the false side of the line, and the other side is the true side. I want to shade the true side. I'm going to keep my graph clean for a second and not going to shade in as much detail as I might have earlier. First part done. Second part, I'm going to graph this. And to make a nicer graph than I might get normally, I'm going to find out where these two boundary lines intersect by doing an RREF A in a second here. But let me just do this to start. So I'm going to first, to do this one, I'm going to graph the boundary, which is 2x plus y equal 10. It's going to be a dashed line. Plug 0 in for x, 0 in for y. Plugging 0 for x, I get 2 times 0 plus y equal to 10. That gives me y equal to 10. So I need to plot the point 0, 10. I'm going to call that the point 0, 10, even though maybe it's not so much the point 0, 10. And by doing this fudging, it's making the point of intersection maybe less important. I'll do the next problem on graph paper and do the point of intersection with a little more accuracy. I'm afraid my graph here is so not accurate that where these two lines intersect, which is a nice point to know, is not going to show up on this graph. It's not terribly important here. Sorry. So now for the next one, if I plug 0 in for the y, I'd get 2x plus 0 equal to 10. Gives me 2x equal to 10, gives me x equal to 5. So that's going to be the point 50, which I'm going to call there. And I'm going to draw that again with a dashed line. And now I'm going to do my shading. So I'm going to take, for my shading, I'm going to do x equal to 0, y equal to 0, into the 2x plus y is less than 10. So I'll go 2 times 0 plus 0 is less than 10. That gives me 0 is less than 10, which is true. So for this line, 0, 0 is down here. This is the true side of this line. This is the false side of this line. So for that line, I'm shading this way. Ultimately, what we'd want to show is where the shadings overlap. So we're going to darken in as dark as we can the region where the shadings overlap. And that's what needs to be indicated for problem 26. It turns out that the rest of the shading that I've shown, the shading that only contains just pink or just green, isn't a region, isn't anything that needs to be shown. And so this would be a picture for problem 26 that would be perfect in terms of for a test. Perfect because I didn't start off with graph paper, so my graphs are moderately accurate. I don't know that this is maybe a good representation of 0, 10 because it looks to me like maybe 0, 10 really should be up there. But for our purposes, I've done everything adequate enough for test purposes. Specifically, I graphed each inequality separately, figured out the x and the y intercepts and where to shade for each one of them, did each one separately, and then I figured out where those shadings overlapped, and I darkened the area the best I could where those shadings overlapped. And that's all that I wanted to do for problem 26. For 28, I'm going to do my graph on graph paper just to make it a little more accurate. And again with the fractions. Ooh. Oh well, I'm living with fractions here, but not happy with myself that I forced these fractions upon you. Sorry about that. So for 28, I'm going to do 2. I'm going to do 4x minus 3y is less than or equal to 10, and 2x plus y is greater than or equal to 10. And I'm going to do all the work on this page, and then I'm going to transfer all my work over to a graph. So specifically, I'm going to get the boundary line first, and it's going to be solid. And for this particular problem, the boundary equation is 4x minus 3y equals to 10. I'm going to plug in 0 for x and 0 for y. When I plug in 0 for x, I get 4 times 0 minus 3y equals to 10. That leaves me with minus 3y equals to 10. It gives me the y equals to 10 over minus 3. So physically, I'm going to write the point 0, 10 over minus 3 10 over minus 3, when I go to graph it on the y-axis, 10 divided by minus 3, I get minus 0.333. So when I go to graph this point, I'm actually graphing the point 0, minus 3.33, and so on. For the next 0, I'm plugging in 0 for the y. I get 4x minus 3 times 0 on the boundary equals to 10. This goes away, gives me 4x equals to 10. Divide both sides by 4, I get x is 10 over 4. 10 over 4 reduces to 5 halves. And I can do that division without my calculator. So I'm going to graph the line that goes through the points 0, negative 3.33, and 2.50. So that's the boundary line. And now I'm going to do the shading before I get over to the graph. And for the shading, I'm going to let x equal to 0, y equal to 0. Plug it into this problem. I'm going to go 4 times 0 minus 3 times 0 is less than or equal to 10. This simplifies to 0 is less than or equal to 10, which is true. So 0, 0 is on the true side of the line. So I'm going to take all this information and transfer it over to a graph, because I brought graph paper to do this, to make a moderately accurate graph. And to even make my graph more accurate, I'm going to enter this as a 2x3 matrix, do RREF. It's kind of not appropriate to do matrices when you have less than's and greater than's, but I'm pretending those are equal to. I'm going to, in addition to plotting those 2 points, I'm going to plot the point where the 2 graphs are going to intersect. I'm going to get the points where the 2 graphs intersect by going second matrix math, entering the matrix that we did a bunch of recently, so hopefully you're still good at those. So I just entered the matrix 4, negative 3, 10, 2, 1, 10, second quit, doing second matrix math, RREF, second matrix, enter, enter. So these graphs, when I graph each line, are going to intersect at the point 4, 2. So in addition, when I go to graph problem 28, I'm going to toss an extra point into my graph, and that's going to be the point 4, 2. So now I'm going to graph those 3 points best I can with graph paper. It makes my graph a little more accurate. So the first point is 0, negative 3.33, and so that's about here. And I'm going to say that's the point 0, negative 10/3. And then I want to also plot the point 2.5 comma 0, which is about there. And I want to plot the point 4, 2, which is about here. Nicely, those things come on a line, and I get to do a solid line. So this would be the boundary line for the first equation, having x-intercept of 5 halves 0, y-intercept of 0, negative 10/3, and having the point 4, 2, which is going to be an important point in some, because it's going to be the point where the 2 graphs intersect. Lastly, 0, 0 gave me a true statement, and 0, 0 is on this side of the line, so this is the true side, this is the false side. And I only want to shade the true side. I'm just going to tell myself I'm going to shade that side of the line and not the bottom half of the line. Drift back to my problem, do the other one the same way. So let me do the boundary. It's going to be solid again, and it's going to be working with the 2x plus y equal to 10. Same deal. I'm going to do 0 for x and 0 for y. When I do 0 for x, I go 2 times 0 plus y equals to 10. That simplifies to y equal to 10, which allows me to plot the point 0, 10. When I let y be 0, I get 2x plus 0 equal to 10. That gives me down to 2x equal to 10. That gives me x equal to 5. That's going to allow me to plot the point 5, 0. And I'm also going to plot the point 4, 2, because it's where these 2 lines intersect, and it's going to be where the 2 graphs cross. And I'm going to force that to come out, but it'll come out perfectly on graph paper anyways. And now for my shading, to figure out the side of the line to shade on, I'm going to go x equal to 0, y equal to 0, into the 2 times 0 plus 0 is greater than or equal to 10. And when I do that, I get a false statement because 0 is not bigger than 10. So for the green line, when I draw it, 0, 0 is going to be the false side. The side away from 0, 0 is going to be the true side. So now I'm going to graph the point 0, 10, 5, 0, 4, 2, draw a solid line, mark the side that has 0, 0 as the false side, the side that doesn't have 0, 0 as the true side, to figure out where to shade. So I'm plotting 0, 10, 5, 0, and I already have the 4, 2 drawn. You can read that. So I'm going to draw through these points, and doing it on graph paper and using a ruler, or drawing thick enough, that would be perfect. 0, 0, we said, is on the false side of this line. So that's the false side of this line. This is the true side of this line. So this line needs to shade this way. Ultimately, what I want to show is where the shadings overlap. And ultimately, I don't need to shade both lines totally. I only need to shade the parts where the shadings overlap, and that's on the true side, and that's going to be this region here. This region up here is the region where the shadings are going to overlap, and that's the region that needs to be darkened. And it's really the only shading that you should show. It's the only shading that you have to show. And so this would be the picture of problem that we just did. Problem number, I guess that was 28. That's the perfect picture in that it shows perfectly the points where the graphs intersect. I graphed both the x and y intercepts of both graphs, shaded both properly, but only shaded so that I could see where the shadings overlap. And that's the perfect ending for problem 28. So I found the x and y intercepts of each, graphed each with solids, also find the points where the two graphs cross, and figured out which side was the true side of each line, shaded the true sides where the true sides overlapped. So rather than having my green graph show this shading and the pink graph show this shading as well, I only showed the shading where the graphs shadings overlapped, and that's the goal for these problems, is to graph both and somehow identify nicely where the shadings overlap. Again, with the really unpleasant fractions, and too small of fractions. But let me just deal with this problem, how it exists, and you'll see why I'm really unhappy with my problem. The x and the y intercepts are both fractions here, and it's going to be so hard to graph this accurately. So let me just change this. 5 and 1, 2. Let me change the top one to 4x plus 2y is less than 22. And the bottom one to 3x minus 5y is less than 10. The bottom one's going to have fractions in it. The top one is not going to have as many fractions in it. Again, I'm not really happy with what I left you for problem 30 because the x and the y intercepts were going to be so close to the point 0, 0 that it just seems silly. So I'm going to do the same thing that I did for the last problem. I'm going to do each separately, like a green side and a pink side. First one, I'm going to work on 4x plus 2y is less than 22. I'm going to graph the boundary, and it's going to be dotted or dashed. I'm going to work with 4x plus 2y equals to 22. plugging in my zeros. If I do the first 0, I go 4 times 0 plus 2y equals to 22. This gives me 2y equals to 22. Dividing both sides by 2, I get y equal to 11. For the other one, if I go 4x plus 2 times 0 equal to 22, this would give me 4x equals to 22. X is going to be 22 over 4, which is 11 over 2, and 11 over 2 is 5.5. In addition, I'm going to RREF, a 2 by 3 matrix with these, and that's going to be where the graphs intersect. So second matrix, edit, 2 by 3, 4 enter, 2 enter, 22, 3, negative 5, 10. Second quit, second enter, enter. These are going to intersect at the point 5, 1. I got that from cheating on my calculator. I'm also going to plot that point. That point's going to be where the green and the pink graph overlap, and it's nice to show that. In fact, in the next problem, it's going to be required to show that. So I'm going to figure out my shading as well before I get to this. So for shading for this one, I'm going to go x equal to 0, y equal to 0. Into this, I'm going to go 4 times 0 plus 2 times 0 is less than 22. This gives me a 0 is less than 22. That's a true statement, so the point 0, 0 is on the true side of the line. So I'm going to draw the point 0, 11, 5.5, 0, 5, 1, and mark the side with 0, 0 as the true side of the line. The side without 0, 0 is the false side of the line. So my graph paper will come in moderately handy here. So first point I want to plot is the point 0, 11. Second point I want to plot is 5.5, 0, which is 11.5, 0. Third point I want to plot was the point 5, 1. Really? Does it really? 11, good. 5.5, good. 5, 1, 20. Yeah, works fine. And I'm going to connect these the best I can. And it's supposed to be dashed. You'll do that when you do your tests. So don't just, if you start drawing something solid and figure out it should be dashed, just make it look like it should be dashed. Or make a note to me, oh, this is supposed to be dashed. If you don't have an eraser, that's handy, because I can't erase with these things. And 0, 0 is the true side of the line. So this is the true side. This is the false side. Now I'm going to come back, and so I'm supposed to shade this way, but I'm holding off to find out where the shadings overlap before I do my shading. Now the ugly fraction one. I just should have done better with these problems, but fractions, again, aren't the worst thing in terms of we should be able to deal with them, although I'd rather not. I'm going to graph the boundary with a dashed line. The boundary is 3x minus 5y equals to 10. Do my zeros, 0 for x, 0 for y. 0 for x is a good one. I get 3 times 0 minus 5y equals to 10. This gives me negative 5y equals to 10. So y is 10 over negative 5, which is negative 2. That's the friendly one. The other one's the bad one. When I go 3x minus 5 times 0 equal to 10, this is going to give me 3x equals to 10. X equals to 10 thirds. And 10 thirds is 3.33. So when I go to graph this, I'm going to graph like 3.33, 0. And I'm also going to graph the point 5, 1. It's because it's where the graphs intersect. That point where I did the RREF is where the graphs overlap. So I'm going to plot the point 0, negative 2, 10 thirds 0, 5 and 1 with a dashed line. And just like the last one, I need to find the side that I'm going to shade on. I'm going to do x equal to 0, y equal to 0. I'm going to go 3 times 0 minus 5 times 0 is less than 10. This gives me 0 is less than 10, and that's true. So 0, 0 for both of these is on the true side. So now I'm going to plot those 3 points and mark the side with 0, 0 as the true side. So the points that I said I needed to plot the point 0, -2. I needed to plot the point 3.30, which I was supposed to call 10/3 0. The point 5,1, which is already there. I'm supposed to draw these with a dashed line. And 0, 0 is on the true side. 0, 0 is up here. So this is the true side, and this is the false side. All the lines have both a true and a false side. And I'm supposed to shade and darken where the true sides overlap. So the true side of the pink line was down here. The true side of the green line was there. So where the shadings are going to overlap is in this region. And this is the region that I'm supposed to darken in completely. This is the region where the shadings overlap. And I don't need to show any more shading than that. Ultimately, in problem 30, the only thing I'm supposed to do after I get each of the lines graphed is darken in the area where the shadings overlap. And if I don't show the shading area where they don't overlap, this section of the green line, this section of the pink line, it's probably better than graphing everything and having it be, it's less messy this way for what it's worth. The next problems are, I almost like them better. They have 4 inequalities, but they all have what I call trivial inequalities. And the trivial inequalities make these problems nice. So problems 32, 34, 36, 8, and 40. The next 5 problems all have the inequality x is greater than or equal to 0, y is greater than or equal to 0, kind of added on to the problems. And these 2 statements make it so the graph, the final shaded area, is going to only exist in the first quadrant. So if I just had these by themselves, this line right here is going to be, this is going to be the y-axis, and I'm going to shade right. Because when you only have an x, you draw a vertical line greater than shades right, and x equals 0 is the equation of the y-axis. The y is greater than or equal to 0 is the x-axis, and I'm going to shade up. So if I wanted to graph this, the x is greater than or equal to 0 is the y-axis, and I shade to the right. The y greater than or equal to 0 is the x-axis, and I'm going to shade up. And if you see where those shadings intersect, those shadings intersect to form the first quadrant. When I do the next 5 graphs, 32, 34, 36, 38, and 40, these 2 parts I'm probably going to not focus on too much. I'll draw the lines, but I won't shade. And when I do my final shaded region, I'm only going to shade in the first quadrant because these 2 overlap to form the first quadrant. And in the next problems, I have 4 inequalities. I want to find out where all 4 shadings overlap. And because these shadings overlap only in the first quadrant, to find out where all 4 shadings overlap, I won't go outside the first quadrant. So that comment, the x greater than or equal to 0, y greater than or equal to 0, is restricting my graph to the first quadrant. So I'm really only doing 2 interesting problems here. I'm going to graph x plus y is less than or equal to 5, and 3x plus y is less than or equal to 9. The instructions in this section, when we have all 4 of these, say to label the corner points. I've kind of been doing that, but I'm going to emphasize what I mean by that here in a second. I've been labeling all the points we need to label already, but I might have been shading over them. So I'm going to, any point that really needs to be featured, I'm going to feature it. So for 32, I need to do the boundary, which is the line x plus y equal to 5 solid. I plug 0 in for x, 0 in for y. These are easy. Plugging in the 1, 0, you get x plus 0 equal to 5. Leaves me with x equal to 5. The other 0, you get 0 plus y equal to 5. And that leaves me with y equal to 5. The points that I'm plotting are 0, 5, and 5, 0. And for my shading, I'll go 0 plus 0 is less than or equal to 5. That gives me 0 is less than or equal to 5, which is true. So 0, 0 is on the true side. I'm also going to find the point where these intersect, doing the RREF, and graph that as well. So I'm going to do second matrix, edit, enter a 2 by 3 matrix, 1, 1, 5, 1, 1, 5 for the top row, 3, 1, 9 for the bottom row, second quit, second matrix, math, RREF, second matrix, enter, enter, and they intersect at the point 2, 3, so I'm also going to draw the point 2, 3. So I'm going to get my graph going. The bottom two inequalities, well, I don't know how much I'm going to show those, but I'll moderately show those. But for this one, I have the point 0, 5, 5, 0. So this is the point 0, 5. This is the point 5, 0. And then in addition, that point I need was 2, 3. So 2, 3. And I get a solid line. I know my shadings only can live in the first quadrant. So when I do my shading, I don't have to worry about shading up here or down here, because the x greater than or equal to 0, y greater than or equal to 0 keeps my shading in the first quadrant. And 0, 0 was true, so this is the true side, and this is the false side. So I'm going to shade, eventually I'm going to shade this down. And I'm not going to go outside the first quadrant because of the trivial constraint, the x greater than or equal to 0, y greater than or equal to 0. Next one, same thing. I'm going to do my boundary, which is a 3x plus y equal to 9. Do my zeros. Plug 0 in for x. I get 3 times 0 plus y equal to 9. This simplifies to y equal to 9. And then the other 0, I get 3x plus 0 equal to 9. This gives me 3x equal to 9, which gives me x equal to 3. And in addition, this is also going to have the point 2, 3, because that's where the lines intersect. Now my shading, finding out the true side of the line, going 3 times 0 plus 0 is less than or equal to 9, gives me 0 is less than or equal to 9, which is true, so 0, 0 is on the true side of the line. So I'm going to plot those 3 points, 0, 9, 3, 0, and 2, 3. So 0, 9 is up here. 2, 3 is already plotted, and 3, 0. And it's a solid line, which is probably the best, because sometimes I forget to do my dash when I'm supposed to. And my shading is supposed to go towards 0, 0, because 0, 0 was a true point. That's the hard work. The other work, if I wanted to show the x greater than or equal to 0, to draw x greater than or equal to 0, it's hard to see the line x equal to 0, but it's the y-axis. And I'm going to shade to the right. And if I want to show the line y equal to 0, hard to see it again. Y equal to 0 is the x-axis, and I shade up. Ultimately, I want to find out where all the shadings overlap. And again, it has to be in the first quadrant because of the x greater than or equal to 0, y greater than or equal to 0. And both of these lines, the green line and the pink line, shade down. The final shaded region is going to be this nice bounded region. This is a nice looking graph in some sense. And the things that are called corner points, this point 5, 0, because it's a point that I've marked and it's along the boundary of the shaded, final shaded region, I call those corner points. So this graph, if I want to darken out its boundary, has 4 corner points. It has the point 0, 0 as a corner. A point 0, 5 is a corner of the final bounded shaded region. The point 2, 3 is a corner of the final bounded shaded region, and that point 3, 0. Those are technically the corner points. 0, 9, and 5, 0 are x and y intercepts, but they're not part of where all the shadings overlap, so they're not technically corner points. So this graph technically has these 4 corner points. So a corner point is defined as a point of intersection along the shaded region boundary. So the boundary of the shaded region I darkened in there, and the corner points I wrote in black. All right. Few more problems, 4 more problems specifically. So again, 34 has the trivial constraints as all these problems do. The x greater than or equal to 0, y greater than or equal to 0 tells me that my final shading can only exist in the first quadrant. And I don't need to do any extra algebra for it. Another fraction problem. So I'm going to do the boundary for the first line. I'm going to do 4x plus 2y equal to 12 as my boundary. Plug in 0 for x and 0 for y. Plugging in 0 for x, I get 4 times 0 plus 2y equals to 12, which gives me 2y equal to 12, which gives me y equal to 6. And if I do 4x plus 2 times 0 equal to 12, this will give me 4x equal to 12, x equal to 3. I'm going to RREF those two to get the intersection point. So I'm going to go second matrix, edit. 4, enter 2, enter 12, 3, enter 1, enter 7. Oh, I did 2 by 4. 2 by 3. 4, enter 2, enter 12, 3, enter 1, enter 7. Second quit, second matrix math, RREF, second matrix enter, enter, and those intersect at the point 1, 4. So I'm going to plot those 3 points. I also need to know the true side of the line. So for shading purposes, I'm going to go 4 times 0 plus 2 times 0 is less than or equal to 12. This gives me 0 is less than or equal to 12, so 0, 0 is on the true side of the line. So as I go to graph this, I'm going to plot the point 0, 6. I'm going to plot the point 3, 0. I'm going to plot the point 1, 4. I get a nice solid line again. And 0, 0 is on the true side of the line. The true side of the line is the side that contains 0, 0. The false side of the line doesn't contain 0, 0. So for this one, I'm going to shade down. And the trivial constraints, the x greater than or equal to 0, y greater than or equal to 0. The x greater than or equal to 0 is that line, and I shade to the right. The y greater than or equal to 0 is this line, and I shade up. Usually I don't even draw those. I just keep my shaded region in the first quadrant to represent those. Next one has some decimals. I'm going to graph the boundary of 3x plus y equal to 7. 0, 0, do 3 times 0 plus y equal to 7. That gives me y equal to 7. And then 3x plus 0 equal to 7. That gives me 3x equal to 7. X equals to 7/3. And 7/3 is 2.330. So when I go to graph this, it's going to be 2.330. And I'm also going to graph the point 1, 4, which is already graphed, but it's going to, my graph's going to go through that point of intersection. For shading, I go 3 times 0 plus 0 is less than or equal to 7. gives me 0 is less than or equal to 7, which is a true statement, so 0, 0 is on the true side. So I'm going to graph the point 0, 7, 2.30, and 1, 4. 0, 7 is going to be easy enough to do. So I have the point 0, 7, 1, 4 is already drawn, and then 2.33, which is 7/3, comma 0. I'm going to just do this, 7/3, comma 0, and then go through those points best I can anyways. And that's another one that shades down, both because this, again, the true side is the side that contains 0, 0, which is beneath the line. So my shading for all my overlapping, I shade in the first quadrant only, underneath the green line, underneath the pink line, and my shaded region is going to look like this. Nice bounded region. The less thans give you sometimes nice boundaries. And this right here, I'm going to mark out the boundary for you a little bit. This is the region where the shadings overlap. The corner points are this point 0, 6, the point here 0, 0, the point there 1, 4, and the point there 7/3, comma 0. The other points that are labeled, the 0, 7 and the 3, 0, because they're not around this boundary of where the shading, all the shadings converge, they're not considered corner points, but if they're labeled on your graph, they're labeled. Mine are labeled anyways, but ultimately this is the minimum of what can be shown. This shows where all four graphs the shadings simultaneously coincide, and I labeled the points where the lines intersect the axes or where the lines intersect each other around that bounded region. So that's the best I could do for that problem, 34. 36 with the greater thans, they're not as nice. Usually with the greater thans, you get an unbounded region, a region that shades out to infinity. So, same problem, but with greater thans, which is maybe kind of nice. So I'm going to do x plus y is greater than 5, and 3x plus y. Same problem as like the first one, I think, greater than 9. I'm doing dashed lines here, so I'm going to get a dashed boundary, and I'm going to do x plus y equal to 5, plugging in 0 for x and 0 for y. So I go 0 plus y equal to 5, which gives me y equal to 5. And then I do x plus 0 equals to 5, which gives me x equal to 5. And I'm going to do the RREF with those two on top of each other to get my third point. So second matrix, edit, 2 by 3, 1, 1, 5, 3, 1, 9, second quit. And those intersect at the point 2, 3. So when I graph the pink, I'm going to graph 0, 5, 5, 0, and 2, 3. And for the shading, this is going to be shading up as opposed to down. So I'm going to go 0 plus 0 is greater than 5, plugging in zeros for the x and the y. And that tells me that 0, 0 is the false side of the line, and the side that doesn't contain 0, 0 is the true side of the line. So when I go to work with this problem, or this part of this problem, I draw the point 0, 5, or the point 5, 0, I guess, and the point 0, 5, in addition to the point 2, 3. And I get a dashed as opposed to a solid line. And it's actually supposed to be line and not a curve, but mine started curving, and it is what it is. And for this one, 0, 0 is on the false side of the line, so I'm going to shade up and away. The true side of the line is going to be up, and when I do my shading, I'm only going to be in the first quadrant, so I'm not going to shade this part of the graph here, or this part of the graph there, because they're not in the first quadrant. That shading is going to be this whole block of the first quadrant. For the next one, I'll do my boundary. It's a dashed boundary again. I'm working on the 3x plus y equal to 9. Do my zeros. For the x equal to 0, I go 3 times 0 plus y equal to 9. That gives me y equal to 9, so I'll plot the point 0, 9. And then 3x plus 0 equal to 9 gives me 3x equal to 9, gives me x equal to 3, so the point 3, 0. In addition, that 2, 3 is also going to be on this. For my shading, I go 3 times 0 plus 0 is greater than 9. That gives me 0 is greater than 9, which is a false statement, so 0, 0 is on the false side of the line. So to incorporate this bit into my work, I do the point 0, 9, the point 3, 0. I already have the point 2, 3 drawn, so I don't need to draw it again, but my graph needs to go through that point. And the true side of the line is the side away from 0, 0. The false side of the line has 0, 0 on it. And so for this shading, I have to stay in the first quadrant again and shade away from 0, 0. So ultimately, the bottom two inequalities just say I need to stay in the first quadrant. And both of these lines are shading up and out, away from the origin, but I can't go outside the first quadrant, so I need to find the region that's simultaneously above the pink line, above the green line, and in the first quadrant. And the bounded region, just darken it in, is going to be this. This is kind of going to be paralleling the boundary, and I'm shading all of this is where I'm shading. So my shaded region is going to have this as a corner point. It's an intercept around the final boundary. It has that 2, 3 as a corner point, and it has this 5, 0 as a corner point. Technically, the point 3, 0 and 0, 5 aren't technically corner points because they're not points where the shadings overlap, or around the edges where the shadings overlap. So these are technically the corner points. Again, but I have the points 0, 5, and 3, 0 drawn, and it's not wrong to have them drawn. So that would be a perfect graph, the best I could do. So usually greater thans kind of shade away from the origin, less thans shade towards the origin. It doesn't have to be that way, but that's kind of the way it often works. 2 more problems. All right. I just really wasn't aware of the fraction avoidance, so I'm dealing with fractions, too many fractions here in problem 38, but I'm just going to deal with them. So as I go to do 38, the first thing I'm going to worry about is 3x minus 2y is less than or equal to 5, and I'm going to do my boundary, which is going to have loaded with fractions. The 3x minus 2y equals to 5, 0, 0. When I do my first 0, I go 3 times 0 minus 2y equals to 5. This gives me minus 2y equals to 5. Y equals to 5 over minus 2, which is minus 5 halves. And when I graph that, I'm going to graph the point 0, negative 2.5. When I do the other 0, I go 3x minus 2 times 0 equal to 5. That gives me 3x equals to 5. Gives me x equals to 5/3. So I'm going to graph 5/3, 0. And 5/3 as a decimal is 1.66. So for this one, I'm going to do 1.6, comma 0. So those are the fraction versions, but I'm really graphing as the decimal versions. I'm also going to graph the point of intersection. So do second matrix edit, 2 by 3 matrix, 3 enter, 3 enter, negative 2 enter, 5 enter, 3 enter, negative 1 enter, 7 enter, second quit, second matrix math, RREF, second matrix, enter, enter. They intersect at the point 3, 2. So I'm going to graph those 3 points, get a nice solid line, and to figure out my shading, sneak it over here, I'm going to see if 3 times 0 minus 2 times 0 is less than or equal to 5. This gives me 0 is less than or equal to 5, so my shading needs to go towards the 0, 0. So when I go to graph these 3 points, 0, negative 2.5, which is about there, I call that 0, negative 5/2, and 1.60, which is about there, and I'm supposed to call that 5/3 0, and 3, 2, which is about there. Solid line looks something like that. My shading is supposed to go that way, towards 0, 0, because 0, 0 is true, so my shading needs to go towards 0, 0, because that's the true side of the line. Again, my shading's not going to go outside the first quadrant, so if I was doing this shading and all by itself and didn't have the other inequality, I'd just do this block right here, because the bottom 2 keep me in the first quadrant. So that would kind of, box out this boxed out that shading. And I'll dig into the other one. Didn't leave myself that much room, but I'm doing 3x minus y is less than or equal to 7. I'm going to worry about my boundary, doing 3x plus y equal to 7, doing my zeros. First 0 is the easy one. 3 times 0 plus y equal to 7 leaves me with y equal to 7. The next one, I go 3x plus 0 equal to 7. This would give me 3x equal to 7. X equals to 7/3, which is like 2.3. When I graph this is like 2.3 comma 0. I'm also going to have the intersection point 3, 2. So I'm going to have those 3 points. My graph is going to stay in the first quadrant. And for my shading, I'm going to go 3 times 0 minus 0 is less than or equal to 7. That gives me a true statement. So I'm going to shade towards the origin after I plot those points. So I'm going to plot the point 0, 7, 2.30. So I have 0, 7. 2.30 is about there. I'm supposed to call that 7/3 0. Whoa. Really? I don't like that. 7, 2, and 1. But look at that. Doesn't. So something's going on here in terms of a math error, because as I do my graph, it's not anywhere close to that point. So something's funky. So let me try to see what's going on here real quickly. That one, negative 2.5 seems good. Oh, I forgot the minus sign. This sign right here, I wrote as a plus, and which makes this part, it's supposed to be minus y equal to 7. It's supposed to be y equal to minus 7. Fortunately, this part won't matter, but the 0, 7 wasn't proper. It's 0, negative 7 that I should have drawn. So I could tell bad things were happening because my points weren't lining up, and my points are supposed to go through. Now it's going to work better. So immediately, because I'm using graph paper and I knew where the lines are supposed to intersect, I could tell that these are solid lines, hopefully, not dashed. Yes, solid. I could tell bad things were happening because it should be the case that all the points that I have commented on should all line up on the same line. And I could see that wasn't happening with that point. So I figured out my mistake. And this green line also needs to shade towards the origin, but I can't go out of the first quadrant because of the trivial constraints. So this green line's gonna, my shading for it's gonna stay in the first quadrant as well, but I'm not gonna go beyond outside the pink line shading. So my shaded region here is going to be this region. It's unbounded, it goes up forever, but it's going to be this little cup kind of region. This is going to be the shaded region where all the shadings overlap. And the corner points are this point 3, 2, this point 5/3, 0, and that point 0, 0. Those are the only points along this boundary that I marked. They're either intercepts or where the graphs overlap. So that would be a perfect graph, at least as perfect I could do, fixing that wrong intercept. Last problem. Getting to be a monstrously long lecture. Oh, this will be my last problem, even though it's not technically the last problem. I know I'm pushing hour and a half or 2 hours, and that's more than I want to do. So I'm going to work with this. 4x minus 2y is less than or equal to 2. And I'm going to do the boundary of 4x minus 2y equals to 2. Plugging in my zeros. Doing my 0 for x, I go 4 times 0 minus 2y equals to 2. That leaves me with minus 2y equals to 2. Dividing both sides by negative 2, I get y equals 2 over negative 2, which is negative 1. Doing my other 0, I get 4x minus 2 times 0 equal to 2. That gives me 4x equals to 2, x equals 2 over 4, which is 1/2. In addition, I'm going to find the point of intersection. Second matrix, edit, 2 by 3 matrix. 4, enter negative 2, 2, 3, enter 1, enter 9, second quit, second enter, enter. These are intersecting at the point 2, 3. So I'm going to draw those 3 points, keep my graph in the first quadrant, not going to shade outside the first quadrant because of the bottom 2 constraints. And then for shading, I'm going to go 4 times 0 minus 2 times 0 is less than or equal to 2. This gives me 0 is less than or equal to 2, which is true. So I want to shade towards the point 0, 0 and stay in the first quadrant. So when I go to graph these, I graph the point 0, negative 1 and the point 1/2, 0 and the intersection point of 2, 3. Solid line for this one, dash for the next one. And because 0, 0 is true, I want my shading to be towards 0, 0. So this shading would just be, that region, basically. And I should label that point 2, 3 better. Now I'm going to get the other graph in there. And I probably shouldn't have drawn what I just drew, but it's there. I'll live with it. Last one's a dashed. So this 3x plus y is greater than 9. I'm going to do the boundary, which is 3x plus y equal to 9. Do my zeros. First 0, I go 3 times 0 plus y equal to 9. That gives me y equal to 9, so the point 0, 9. And then 3x plus 0 equal to 9 gives me 3x equal to 9, which gives me x equal to 3. And in addition, I want the point 2, 3. So I'm going to graph the point 0, 9, 3, 0, and 2, 3. And then for my shading, I go 3 times 0 plus 0 is greater than 9. That gives me 0 is greater than 9, which is false. So the side of the line that has 0, 0 is false. And I want to shade away from the origin. So I'm going to plot those 3 points, 0, 9, 3, 0, and 2, 3, which I already have plotted. This is supposed to be a dashed line as opposed to a solid line. And this line is supposed to shade away from the origin. The trivial constraints keep me in the first quadrant. And so the bounded region I'm going to worry about is this region, the region in the first quadrant that the pink shading and the green shading overlap. The pink shading needed to go towards the origin. The green shading needed to go away from the origin. So this region up here is the region I'm worried about. The corner points are only these 2 points, the 0.09 and the 0.23, because in that region, those are the only points that I've marked. The other points that I marked are intercepts that didn't come in the final shaded region. So by my vote, I'm skipping the last problem because I know that this lecture is getting monstrously long. If you try the last problem and want to know if your answer is right, come visit me and I'll look at your work and give you an idea if you went the right way.